Welcome to the fifth lecture on metal activity series. And what we're going to be looking at here is the idea that different metals have different reactivities. And if you have experienced this before, and if you think about some commonalities in terms of history, we understand that some metals are more reactive than others. For example, why is it that gold was found first? It's a native metal that has always been around, and same with silver. Well, the reason is those aren't very reactive, and so they are found in the native form in the ground. Whereas other metals, such as aluminium, was so reactive that it caused ores. It was the formation of ores, and we didn't know aluminium was around until we could extract that. So some metals are more reactive than others, and we can use that property when it comes to redox and electrochemistry and making batteries. Okay, so we have seen this concept before, where we do metal displacement reactions, where the more active metal displaces the less active metal from solution. And so that's one way in which we can test how reactive metals are. And so let's just do that. Let's say we have a piece of zinc. Now we have a piece of silver, have a piece of magnesium and a piece of iron. And we place those into copper sulfate. When we do that, we're going to notice that some react very, very quickly. For example, magnesium is going to be rapid reaction. We're going to get a decolorization of the copper, and we're going to get the copper plating out on the magnesium, and so that's going to be a rapid reaction there. So magnesium is very reactive. It's going to lose its electrons and give them to copper. Copper is going to turn to copper solid and form on the outside of the magnesium. Okay, and so we're going to have a metal displacement reaction there. Magnesium's oxidized. Then what we're going to notice is we're going to see that zinc is also going to do the same sort of thing, but not as rapidly as magnesium. So it's going to get a growth of, or a deposit of copper on the outside of the zinc, but not as rapidly as our magnesium. So I guess we can put medium there. Then we're going to see that iron is going to do the same, but it's going to be very slow. And then the slowest of all is going to be silver. Okay, very little or to no change, because silver is not very reactive. And so we've now got to order, if we were to go the most reactive to the least reactive, we could say that the most reactive here was magnesium, and then we can say it's more reactive than zinc, which is more reactive than iron, which is more reactive than silver. So we have a series here of metals that show different reactivities. So up here, the most reactive are those that are easily oxidized, while down here, the less active ones are harder to be oxidized. Okay? And so we can come up with a series. Now, of course, we can react them with other things as well. Another typical example is now say, okay, well, let's now put them in acid and see how their reactivity goes in acid. And we're going to find a similar reactivity here. Now, why do we react them with acid? Well, now, in these ones here, we're comparing it with copper, right? So we had, let's just do the most reactive. So we had magnesium. We had that with copper, iron, in solution. And then the magnesium gave lots of electrons, so it was oxidized, and therefore it became an M2 plus, and copper was reduced. So we had a redox reaction. Then in the second one we had the zinc. The zinc solid did the same thing. The zinc lost electrons, so it was oxidized to form the iron, Zn2 plus, and then it plated out copper. So they were very rapid, right? Rapid, medium. Then we had the slow reaction. The silver had no reaction. So we could do the same thing with acids, and so we could put an H plus here. So if I was to do magnesium and I was to put that in hydrochloric acid, so let's just write H plus now instead of the hydrochloric acid, because the Cl does nothing, it's a spectator ion, right? And so what happens is the magnesium will lose an electron to hydrogen, and it will form the same thing, H2 plus, and the hydrogen gets reduced to hydrogen gas. So we better put a 2 there. And so we've got a 2 plus on this side, a 2 plus on that side, 2 hydrogens here, 2 hydrogens, and of course the magnesiums. So we've got a sort of a balanced equation there, if you will. And so magnesium has been oxidized and the hydrogen has been reduced. And so we have our typical our hydrogen there that we test with the POP test with metal acid reactions. So what we can do is we can do the same thing. We can get our metals and react them with hydrogen to see how well they react with hydrogen. Then we can do it with water, cold water, hot water, etc. And by mixing them with different reagents and seeing how easily they become oxidized or they react, we can build up an activity series. And one's going to flick up right here. And as you can see there, we've got a whole list of metals with hydrogen as a comparison because we have hydrogen here. And that series shows the most reactive at the top, the most easily oxidized. And as you go down the list, they become less and less reactive until you get down the bottom where you got like platinum. Platinum is a very inert metal. It does not oxidize very easily, and so therefore it's way down the bottom there. So that's called the metal activity series, and very, very important. Now, of course, we can get values now. If we wanted to use a standard, we could use a standard to compare the values and get actual numbers, and we can generate what's called a reduction potential. And you've probably seen a lot of textbooks a standard reduction potential table, and that's going to lead a little bit more into batteries. So that's what we mean by the metal activity series. I'll see in another video when we look at the actual electrode potentials and talk a bit about that leading on to batteries. Anyway, have fun with chemistry, and I'll catch you in the next video.